estimation for missing data. So it's been a really good discussion. And thank you so much for your presentations and the careful preparation. I think you'll find Dr. Cleveland to be a fantastic communicator of very complex ideas in a way that we can all understand them. It's sometimes very challenging for me to get the quantitative methods, and appreciate the way you communicate. So Dr. Cleveland is at Penn State University. He is affiliated with the Prevention Research Center there. Works with Rob Teresi, who's a colleague of Joel's, and potentially mine someday. We wrote a proposal together this year, so we'll see what happens. He has been at Penn State for a number of years. Was with the Methodology Center
2006
since 2006, and went there as a postdoc. Prior to that, he was at Iowa State, where he got his PhD in Human Development and Family Sciences.
Right? Family Studies.
Family Studies.
HDFS.
Which is sort of the intersection of sociology, psychology, and a few other sciences, as I understand it.
Right.
And then prior to that, you had other training in methods, right? In quant methods?
I had a stat minor at Iowa State.
Okay.
When I was getting my PhD.
Prior to that, I was a pharmacy school graduate from Creighton. So he's actually a really good consultant for us on our work looking at the interprofessional communication to prevent prescription drug misuse. So we're delighted to have you here for the second time, and I'm going to turn it over to you at this point so that you can tell us all about multi-level model.
All right, well, thank you. So this is my third talk today, so if I struggle a little bit, in the last presentation, one of my slides, so if you've been here for all three, you'll notice a very similar kind of structure and pattern to my slides, and a lot of copying and pasting. So in the last presentation, there was actually one line that got copied from one presentation to the next. So I hope that I don't start talking about missing data or Monte Carlo simulations or something in the midst of this talk, because it will totally confuse you. But just be aware that things could happen. My mind is probably going in many different directions trying to keep track of all this, but I appreciate the opportunity to come down here. As Dr. Pack mentioned, my research interests really, I think, align very well with what you're doing here, and it gives me a chance to kind of pull some of my thoughts together to present them in ways that are understandable to all of you, because a lot of these are issues that we all deal with, whether it be missing data or whatever, but oftentimes don't have the time to really think systematically through. So the last couple weeks when I had the chance to kind of pull those things together, it helped kind of solidify things in my own mind. For this talk, for multi-level modeling, the same process kind of occurred, but I had at least some resources to draw upon. The resources were that for the last 2 years I taught a graduate level multi-level modeling class at Penn State. So a 16-week course. And so my challenge was, in deciding how to proceed in this talk, was how do I even begin to fit 15 or 16 weeks of information into an hour and a half talk? So my first thought was, well, maybe I could make it 3 hours, and I can, divide this into 2 talks or something like that. And then I thought, no, that's asking too much. I think I can do a little bit better. But we'll see how that works at the end, because the whole idea is hopefully to make this conceptually understandable to those of you who have maybe never even looked at multiple or multi-level models or hierarchical data, at the same time as providing information to those of you who probably have some understanding of multiple levels and these types of analyses. So I want to kind of strike the balance between kind of introducing new ideas to some of you who I'm guessing have never heard of these things, and at the same time also give you some practical examples of how to apply these in the real world. So the caveat being that this is a very condensed version of a 16-week course that I would recommend if you have the opportunity. I guess apparently last semester there was the opportunity here at ETSU to take a multi-level class in psychology. Is that right? So hopefully, if you are not in that camp who's been exposed to these, this will be a, kind of an impetus for you to learn more. And I'll give you some resources at the end for learning more on your own. So I've titled this with the subtitle of It's Just Regression. And the idea behind that is that everything that I talk about today, hopefully in this presentation, should be something that those of you who have had some experience with regression are familiar with. So who knows something about regression? Almost everybody, right? So we all should be able to follow along this talk. That's the goal. We'll see if I succeed. So here's the kind of the outline, the general goals. We'll give you this very brief, hopefully brief, conceptual introduction to multi-level modeling, abbreviated MLM, or sometimes hierarchical linear modeling, HLM, kind of two sides of the same coin or the same concept with different names. And then go through two specific examples of using multi-level models or hierarchical models in two kind of scenarios. One scenario being what I'm calling clustered data, like a school-based sample, and then another scenario where you have longitudinal repeated measures data using an individual growth modeling example. And then at the end, I'll provide some resources for doing these things on your own. So in this particular talk, if I remember correctly, what I did last night, I think I took out all of the SAS syntax. Yeah, because I just felt that was a little bit too overwhelming. So if you want the previous version of this presentation, I can send you that has SAS syntax for running these models. So I will not get into that level of detail of showing this is how I'm going to run this model in SAS. I'm going to more focus on the conceptual ideas behind it, give you the results of some studies that I've been involved with or seen, and show you the results, and maybe more importantly, guide you through interpreting the results. How do we interpret this parameter when we know it's a multi-level model? What's this mean in this situation? So that's kind of where we're going to focus. So the first question is, and this relates back to my training in HDFS, Human Development Family Studies, why do we even need multi-level models in the first place? If it's just regression, why can't we just stick with what we learned in Regression 101 or 401, whatever? Why do we need to go through all of these extra painful steps? And the idea is that in reality, in the real world, nesting is the true situation, that individuals are nested within groups. This example here comes from the kind of the HDFS 101 concept of Bronfenbrenner's ecological systems model. Some of you may have heard about that. It's the idea that you can't just study an individual, like a child, without also accounting for all of these other systems and things that are happening in their world. They are part of a family, they have peers that they interact with, they probably go to a school, they live in a larger community that's part of the larger world. And all these arrows are depicting the idea that all these multiple levels are interacting. So as we were talking this morning about substance use. So substance use is a oftentimes byproduct or a outcome that may result from environmental conditions of living in high poverty contexts or situations where job unemployment is very high. So that larger environment has an impact on the individual outcome. And so you need to take into account the fact that all of these interactions are occurring all the time. And so we need some way to account for these different hierarchies. We can't just focus on individual behavior. So this is the idea of psychology and sociology kind of coming together. Sociology focuses on basically the impact of communities and schools on individuals. Psychology focuses on the individual here, and HDFS, my perspective is that you need to account for everything as much as you possibly can. It's difficult and sometimes impossible, but you can do your best to try. So, more, I guess, concretely, why do we need multiple levels and multi-level modeling? These are some examples where we're going to find this nested, clustered structure. So I chose an example based on the DIDAR study. What if we have 3 patients who are patients of physician 1, and we have another 3 patients who are patients of physician 2. And the question might be, are these patients that are patients of physician 2 more or less likely to be prescribed opioid analgesics compared to other physicians? So the idea is that patients are nested within physicians. So we have 2 levels of data here that we're dealing with. We have one level of individual patients, and they're nested within multiple physicians. So you can imagine this physician being 1, 2, all the way up to whatever number of physicians are possible, 30 or 100, whatever your sample is composed of. Another example, we can have individuals that are nested within neighborhoods. So you belong to a certain neighborhood or a community, other people belong to other neighborhoods and communities. And so we can ask questions like, what's the effect of neighborhood poverty on individual health? Because we know that there are risk factors, neighborhood level risk factors, that have impacts on substance use and health and other outcomes. So we need to account for the fact that individuals belong to certain neighborhoods. Finally, another example, students in schools are often nested within classrooms with individual teachers. They themselves are nested within schools, so we have multiple levels of hierarchies. So now we're seeing a case where we have 3 levels. We have students at level 1, individual classrooms at level 2, and then schools at level 3. And we can imagine variables or constructs that are defined at each of these levels. So you can imagine the relationship between student performance and maybe teacher experience. Maybe students who are attending classrooms where teachers have more experience do better than students who the teacher has no experience. Or teacher burnout could be a teacher characteristic. And then all those things can also be dependent on school level characteristics. Maybe these relationships differ between public schools and private schools, or schools in high risk versus low risk environments. The point being is that once you start looking for these hierarchies, you're going to find them everywhere. So that's the danger, I guess, of this. You're going to see the need for this probably more often than maybe you would like to. But the idea is this is reality. This is how things are in the real world. And multi-level models allow you to start accounting for these hierarchies. So this is just a slide to show you that there are many different hierarchies that I'm sure all of you can imagine. We won't go into those possibilities. One final example in our second kind of case scenario, we can also imagine that when we have repeated measures, longitudinal data, we can also treat that as another level of a hierarchy. So when we have a study that follows individuals for 3 time observations, we can treat these 3 time observations as a hierarchical level nested within individual persons. And then of course, the idea up here is there can be 3 levels or more up and beyond. We'll focus on just this idea that individual observations can be nested within a person using growth models in our second example. Okay, so once again, the question is, why do we go to all this trouble? Why can't we just stick with regression? We all have learned it, we're comfortable with it, everything is fine. 2 reasons, one statistical, one more conceptual. The statistical reason is that the correlations within the groups must be accounted for, or should be accounted for. When we have individuals that are nested, individuals within groups are more alike than individuals in other groups. That's the basic idea. When we said that those students in one classroom with one type of teacher, those students are more alike than they are to other students in another classroom. And so because of that nesting structure, there's going to be problems with correlations within those groups. So we'll come back to that in the statistical description after we talk a little bit about effects at multiple levels. This is more of a conceptual need for accounting for multiple levels. And that is the idea that if you don't go to all this trouble, you must assume that the same model applies to the larger unit. So when we have students nested within teachers, nested within schools, or individuals nested within neighborhoods, if you didn't take into account all those hierarchies, you're left with the assumption that everything is treated the same. The problem is that there are types of fallacies or falseness that results from interpreting at the wrong level. When you have hierarchical data, the relationships among variables at one level may be different than the relationships of the variables at a second level. The most kind of common example that I've seen for this type of what's called ecological fallacy, let me see if I can remember this correctly, is to imagine the relationship between income and, let's say, cardiac health, or some type of indicator of coronary artery disease or something like that. So the relationship between income and health in general, let's say. At the individual level, we probably would imagine that there is a positive relationship between income and a person's cardiac health, right? We know basically that if you have lower income, you're less likely to see physicians with preventative measures and other outcomes related to poorer health if you have less income, right? Everybody kind of go along with that idea? If you look at epidemiological data, however, and look at the level of a country, a lot of studies will show that countries with higher average income across a population actually have less health outcomes. So that there is a relationship between having higher income, like more industrialized countries, and higher incidences of heart disease or heart attacks. So there seems to be a different type of relationship there between the individual and the country. So if you are not sure like how these things are all working together, you might interpret the relationship between income and cardiac health one way depending upon what level of analysis you're working with, at the country level or the individual level. And there's many examples, I think, in health that you could probably think about that, where the relationship between individual factors is different than epidemiological countrywide or nationwide relationships. So the idea is that these can lead to different conclusions. You need to be aware of what level you're kind of concerned with. And also they can interact. That income of a country can affect a person's individual income, which can affect their health. So all these things are working together. If we move to the second part of why we need this is the statistical need relating to the correlations within groups that I mentioned. And this is where we are reminded that once again, we're just dealing with regression. So what I've shown here is hopefully a familiar slide. It's actually what we showed earlier this morning. Of the relationship between some variable X and some outcome Y. So this is the depiction of a regression line. We see that Y for an individual is a function of an intercept, a slope, and some random residual. I think I go through all that. So yes, the standard regression is defined by the intercept, which is defined as where X equals 0. We have the regression being a function of the beta 1, which is the slope, which is basically, you remember, the change in Y as a function of the change of X. So everybody familiar with those, right? And then finally, the last part of a normal regression is this idea of the residuals, the difference between the fitted regression line and the actual observation. So in least squares regression, we're trying to minimize this residual variance. We're trying to fit a line that best fits those observations for that individual. So these residuals, these error terms, are what's the problem that we encounter when we have hierarchical data, when we have multiple levels of data. In the standard regression model, one of the most basic assumptions is that those errors are not correlated with each other. When you do a regression analysis, you make assumptions about those error terms that they are all independent. There's that independence assumption that you kind of proceed with. When you have multiple levels of data and you have students nested within classrooms or individuals nested within neighborhoods, that assumption of independence is violated because those individuals in that classroom have some degree of similarity that they share, that other individuals in another group don't have. They share another set of similarities. And so because of that nested structure, those individuals within one group have some dependency on each other. So if we're imagining students in a classroom, because of that teacher's level of experience, maybe their outcome on some reading achievement score is going to be affected by that teacher's abilities or that teacher's characteristics. And another classroom down the hall with another teacher, their outcomes on that performance test might also be different than another classroom's. And so you have to account for the fact that individuals are all within these groups, and individuals within a classroom share some kind of similar characteristics, or individuals in a neighborhood all share some kind of characteristics. So they're dependent on each other, they're not independent. In other words, like a normal regression would assume. So because of that, we have standard errors, which are measures of variance or variability that are too small. How much of this is a problem is defined by a statistic called the intra-class correlation, or the ICC. So we're going to talk about the ICC as a way to tell us how much dependency is there in this particular group relative to another group. So we're going to use this ICC, and it's kind of the key to understanding the reason for these multi-level models. So the ICC is telling us the degree of similarity between lower level units that belong to some kind of higher level groups, and it provides a measure of how dependent those observations are for that particular group relative to the observations in another group. So the formula for calculating ICC is something that also should be somewhat familiar. This is basically an ANOVA. The between group variance divided by the total variance, the between group plus the within group variance. We're going to use that to determine the degree of dependency within our observations. So I imagine that right now some of you may be a little bit confused, struggling, because we've already introduced some kind of equation here, and I promise no equations, or did I promise that? Good, because it's not possible. So let me walk you through a little bit more about this ICC to help kind of understand it, because this is really the key to understanding why we need multi-level models in the first place. So imagine this. This is like a histogram. It's kind of turned on its side. So if you turn this way, this would be the values from 20 to 140 of some sample of some observation. It just happens to be tilted at an angle. So this is the distribution of responses to some item that asks, maybe like, I don't know, we wouldn't say IQ because people, well, I guess people could have IQs of 35. Mm-hmm. Let's think of something more positive. Whatever our outcome variable is, this is the distribution of responses. The mean is equal to about 90 or so. We have a standard deviation. In this case, we had a sample size of about 1,000 people. So that's just kind of a generic full sample distribution to think about. We can simplify understanding the multi-level model by breaking down this distribution. If we know we have groups of people clustered within our full data set, we can think about how the distribution of this outcome variable might vary within those groups. So I'm going to simplify this full sample distribution that had 1,000 people into imagine a scenario that looks something like this, but instead we only have like maybe 10 or 12 people or 15 people. And those people are nested within 3 groups. So let's say this is 3 classrooms, classroom 1, classroom 2, and classroom 3. And each of these groups has 3 individuals or 5 individuals, 3 to 5 roughly within each group. So we're depicting first classroom in the blue, second classroom in the yellow, and then the third classroom in the purple. And this is just showing on that same scale the average or the responses for individuals in that group. So it appears, let's say that this is maybe some kind of standardized score on reading achievement or something like that. Students in this classroom seem to be all doing very well. They're ranging from like 110 to 140. Students in this classroom are somewhat in the middle of the distribution, and these poor students down here who have a teacher who's burned out and doesn't feel like teaching anymore, they didn't do so well. So we're going to use this breakdown to help understand the ICC. The question that we start out with is, we want to know like the average outcome of that standardized test score or whatever. So one way we can take a guess for what the average outcome in my sample of students in these classrooms would be to just calculate the overall average. The mean of y would be a good best guess for saying what's the average standardized score for this reading achievement test. And then we can simply calculate what's called the grand mean, which is just simply the mean over all of the individuals in my sample. In this case, it equals 89.55, so that's depicted by the red line. So that's one way to say what's the average score for this particular sample. The problem is, we just saw in that previous slide that there seems to be some effect of belonging to different classrooms or different groups on what a person's score was. So if we're just relying on the single grand mean, we're going to be overestimating in some cases, and in other cases underestimating, and sometimes wildly off in terms of a best guess estimate for what a student's average score for that test may be. So we can take advantage of these nested hierarchical groups and compute the average value of the outcome within each group. So if these students in the blue group were combined and estimated the average mean within that group, we would depict that by this blue dashed line here. We can also compute the average score for the third group here and depict it by the purple line here. It's hard to see in this example, but there's a yellow line right below that red line there that shows the mean for the second group. Okay, so what we're doing basically is we're taking advantage of the fact that individuals are not independent. Individuals belong to groups, and so we're going to compute an average score for each of those groups and show that with this dotted line that depicts what are called random intercepts, or values for each group, 3 different group means. And now we are using those group means to compute the ICC by basically dividing the variability in our outcome into 2 separate piles. There's a between group variability and a variability that's within groups. So we're decomposing the variance into 2 sources. Between group variance is the difference of each group from the grand mean. So notice that these lines here are showing that the difference between this group's overall average and the grand mean is depicted by this, I guess, double-headed arrow here. There's also a between group variability between this group and the overall grand mean, depicted by this double-headed arrow. And then there's also a very little amount of variability between the yellow group's overall mean and the grand mean. So that's telling us how different each group is from the overall average. So that's the between group variability, the differences between group 1 and group 2 and group 3. But we also have variability within groups. There's differences of each individual from their own group mean. So that's depicted down here by these double-headed arrows. So this is showing, in this case, this particular observation is different from the group mean, as well as this observation, and same thing repeated for each group. So we have variability within a group that's captured within the within group variance, and then we have differences between groups depicted by the between group variance. And these two amounts of variance, or these two piles of variance, are what we're going to use to determine the ICC, which is the key to understanding why we need to use multi-level models. We have two scenarios here I'm going to talk about. First of all, a reminder, this is our ICC formula, the between group variance divided by the between group plus the within group, which basically equals the total variance in our outcome. So on the left side is an example of a large intra-class correlation. So this is what we just saw. There's a lot of variability between the group mean and the overall mean. So this variability between the purple group and the overall average, and the variability between this group and the overall average is fairly large relative to the differences of within individuals and the group mean. So there's between group variability depicted by the dotted line, the difference between the dotted line and the red line, and then within group variability depicted kind of within here. These all seem to be clustered together, in other words. So these are all fairly close around one single number. These are all fairly close around another number relative to the differences between each group's overall average and the grand mean. On the other hand, we might have a situation where we have a smaller ICC where the relative amount of variability is greater within groups than it is relative to between groups. So in this case, here's our grand mean once again overall. And now when we look at the blue group, here's one observation, here's another one, here's another one, here's another one. Now there seems to be a lot of variability within the blue group around their own group mean. The same thing is true with the yellow group. There's more spread between observations within each group relative to the difference between each group and the grand mean. And as a result of that, the ICC is smaller.
Excuse me. So I was curious, why do we categorize small and large ICC? Why can't we use the F distribution and just really say it's a significant F score versus not?
Well, what we're going to do is account for the multiple levels in an unconditional model, because we want to be able to divide that between group variability and the within group variability and get a measure of how large that ICC value is.
So that's what the F test will tell us.
Yes, but the F test in a normal ANOVA would not be able to take into account multiple levels of hierarchies. So the dependency of the data itself needs to be accounted for in the hierarchical model to divide the nested structure within groups and between groups.
Right. I'm right there. So
Yeah.
I agree with there are obvious reasons to classify in multiple groups. My point was why we just look at ICC, and ICC's calculation is important. Why we just look at the large versus small? Why not we just use ICC values to see whether it's significant or not?
I think this is just an illustration of large
Yeah.
and small. I think it's not. There's no particular category of large and small like Cohen's effect size
Right.
or something. This is just an example.
Yeah, and that's the bottom line too, is that what is a large enough ICC to justify using a multi-level model? The literature is open on that debate.
See, that's what my point is. If it is large enough to be significant, then it justifies using HLM.
Right.
If it is not large enough to be significant, then
Most people would say that that's not true. Most people would say that any correlation within the data, any ICC value, whether it's 0.01, 0.02, usually the cutoff rule of thumb is 0.05. Even in those lower values of ICCs, you still have dependency in your observations that need to be accounted for. It's going to affect your standard errors. If you don't take that into account, your standard errors are going to be affected. And so this has to be accounted for using multiple levels in your analysis.
So regardless of being large or small, ICC does influence, so we should always account it.
Right, yeah, so ICC is a kind of a first step to see how much dependency there is within my data, but a lot of people would say no matter what that ICC value is, unless it's 0.000, you need to account for the multiple levels of your data to properly estimate your standard errors to get true results.
Perfect. Thank you.
And especially because these methods are now so easily implemented, why not do them?
Yeah, yeah.
Why not take into account that multiple level and just
Makes sense,
move forward?
absolutely.
Yeah, definitely.
So Michael, if I'm understanding this correctly, even if the same formula, there's really a different purpose. The ANOVA is to see if there's differences between groups.
Right.
Whereas this is to really try to predict individuals' behavior, taking into account the groups and stuff they come from. So they have very different purposes, which is what's separating how we're going about this.
Right, yeah, and also the idea that when we get into these multiple levels is that maybe you want to have interactions between individual level variables and group level variables, and we'll show you an example of that. So in that case, if you didn't take into account the clustered hierarchical data structure, you would not be able to separate those two types of effects, individual level effects and teacher level effects.
Right, so one's like weighing cards, and the other one is like looking inside the engine to see what's really making the baby.
I guess,
better.
yeah.
That's the way I think of it.
Yeah.
So, I mean, previously I've heard of using like a 0.05 or 0.1 cutoff for ICC because once you get into your multi-level, you're sacrificing parsimony and potentially, so, I mean, is there a balance between the parsimonious fit of your model and this ability to account for whatever clustering?
There's always that trade-off, I guess, of parsimony, but I would say that, once again, if you have the nested data, and you are interested in any type of group level, higher level effects, then it's much better to just move forward with a multiple level approach and go with it. If you're only interested in individual level variables and outcomes, then maybe not accounting for that multiple levels is a more parsimonious model. But once again, the idea is that in SAS Proc Mixed or SPSS, it's so easy and straightforward to just account for that. And actually we'll give you a number to tell you how important that variability is. Why not just go ahead and do it? Just, cover your bases, I guess. It sets you up for future things anyway, that it just makes sense to go ahead and do it. So I would say parsimony kind of becomes less important to me in that case than truly modeling the real world situation that I have before me. Because there's always going to be some type of dependency.
So can I just add something? So in order to be able to analyze it according to multiple levels, we do need some kind of identification, right? For the different levels, unless it's time, it's
You do not need in SAS or SPSS to tell SAS or SPSS what level your variable is. SAS or SPSS will automatically know how to handle that variable as long as you set your data up correctly.
that's right.
The correct thing to set your data up with is you need some kind of identifier for a group.
Yeah, that's what I mean. Is you need to identify like an ID.
Yeah, you need an identifier that tells you, like if we're studying students in classrooms, we need to have an ID for an individual student. So student 1, 2, 3, on down to 30. And then all the students in the first classroom are going to have an ID number for teacher 1.
One, right, yeah.
And then students in another class are going to have an ID number for teacher 2. Or whatever your grouping variable
Yeah, that's
is.
what I meant.
Yeah, so as long as you have the data structured that way, then SPSS and SAS will know that that's the way, that's where that variable gets entered.
So, I mean, this is, at the risk of confusing things here for a second.
What happened to my slide?
Hit your button and see what happens. Oh, no.
Yeah, you might want to just move the mouse.
So what about the situation where you have missing
My
subjects.
power just went out.
Oh,
My
wow.
battery, but I brought a cord. I didn't even think about looking at the battery reserve. This is a good time for a question.
Yeah. Let's see if, how well you multitask and get your,
Keep talking.
Well, what about a situation where you have multiple missing subjects, or I guess differential missing subjects between classes, for example? I guess you'd have to bring two of the topics today to bear.
Oh, okay, I see what you're saying. So if you have missing data,
Yeah.
and your data are nested within
Nested,
groups,
right.
how do you properly account for that?
Yeah.
That's a good question. That a lot of people would say one way to handle that is to impute within each group and then combine together. But I don't know if there's a bottom line, only do it this way or not. But I believe what I've seen the latest in regard to that, hopefully this comes back on. Do I need to do something for the outlet up here?
Is this not working?
Turning on. I'm not getting, no, now we got a green light.
Okay.
I guess my laptop has been on all day, hasn't it?
When are you going to run out of town?
About 4 o'clock.
So you would do imputations or multiple imputations for each of the cells, basically.
Yeah, you could either do it separately by group, or you could have a dummy variable if you have a smaller number of groups. I don't know what you do. I honestly don't know what you do if you have 30 groups. It seems like a very major problem because you're likely to have missing data that might depend on what group you belong to.
I just imagine, so when you do school-based research, different classrooms are going to have different levels of attendance per day, right?
Yeah.
That's just the way it goes. So. And you would imagine that those are not random, right?
No.
Right.
That's one of those things that I think understanding patterns of missingness, that if missingness depends on some variable like the class that you belong to, building that into your imputation model as best you can.
Can you just model that, Michael? Or
Yeah.
Can you just model all that in certain ways?
Yeah, you can see if there's missingness that depends on classroom level variable or something, or classroom identifier.
Yeah, that's the first place to start again.
I think I'm wait.
Beach, I guess.
So yeah, I guess I'm back on track. So I don't know if that totally answered your question.
Yeah, it did.
So are we comfortable with the idea of ICC? Basically, once again, I didn't mention that it ranges basically between 0 and 100. So this kind of gives you two examples of situations where we have large ICC, small ICC. The bottom line is that any type of clustering is going to probably result in some ICC value, and the cutoff points 0.5 to 0.1 is often used, but I believe that if you have any type of ICC, it's better to just go ahead and account for that level of nesting and just move forward from there. But this at least gives you some idea of how dependent groups are within each other. So if we're comfortable with that, let's move forward to how we're going to build this multiple-level model, this multi-level model. So we have to go back to our regression first. So we're going to, once again, begin with ordinary least squares regression, where we have a regression line fit between these observation points, resulting in our familiar regression equation. So I don't think there's any way to teach multi-level modeling without equations. So I apologize if you're not familiar or comfortable with that, but this is I think the only way to understand it. We'll try to make this as straightforward as possible, knowing that this is our regression equation of an intercept, a slope, we have residuals of the differences between observed data and some kind of fitted regression line. What if we had a scenario, once again, where we have collected data from more than one group? So we have 2 different schools or 2 neighborhoods on down the line. If we fit that regression model, and here we have depicted the 2 groups with different colors and types of dots, we can fit a normal regression model using a single model and fit a regression line through all those observation points. But once again, we notice that there seems to be some group differences, right? The red diamonds are different than the gray circles in that there seems to be some dependency of error depending on the group that you belong to. All of the individuals in the red diamond square have values less than the predicted line. All of the individuals in the gray circles have observations, other than this guy over here, I guess, have positive differences, right? So if we look at error residuals, there's dependency now, right? All these observations have negative values. Most of these have positive values. That's not random, in other words. We violated that independence assumption. We need to somehow account for the fact that we have 2 groups of people, or 2 sets of observations. That is not available in this single level model. We could then maybe just fit 2 regression lines. Maybe if we have 2 separate groups, then why not just fit 2 regression lines? 1 regression for the gray group, 1 regression line for the red group. That makes everybody happy, right? Now we've basically got random errors around this line, we've got random errors around this line. So we're doing a good job of maintaining independence of residuals within groups. And we could even indicate what group they belong to with some kind of dummy variable. So maybe we could add a variable G to indicate whether the individuals belong to group 1 or group 2, 1 or 0, and then use that estimate to basically tell us the difference between the 2 groups. The problem with that approach is, what if we have 30 schools or 35 schools? Are we going to have 34 dummy indicators to tell us what group they're in? And we need to start taking into account interactions between group variables and the effect of X on Y. That's going to become very unwieldy very quickly, which leads to the need for multi-level modeling, which is going to allow you to answer all of these different types of questions or address these different types of analyses within one model. It's going to allow you to identify average outcome differences between group 1 and group 2. It's going to tell you whether the outcomes vary among persons within groups with different individual level attributes. It's also going to allow us to model differences among groups, including model differences in outcomes that are associated with individual level traits. In other words, if we have individual attributes that affect that outcome variable, does that relationship differ between one group and another? So multi-level modeling allows you to address all of these kind of questions in one single model. Now this is where things get a little bit hairy for the equations, so we'll see if we can walk you through this. We're going to build a multi-level model by having 2 levels. In this case, we're going to deal with just a multi-level model that has 2 levels of data. Students nested within a classroom, or patients within doctors, or individuals within neighborhoods. So we're just going to deal with 2 levels for now. So we're going to build a 2-level model. We're going to start with a level 1 model, which is our familiar regression that we've seen many times. But now we're going to add a subscript for J. So normally we have yi as a function of all of these terms. We're going to add a subscript for y individual nested within J group. And each group has its own intercept coefficient and its own slope coefficient for whatever individual level trait we have. So our outcome variable, we're saying that yi is a function of an intercept and an effect of x, and then some kind of random residualness. That's what we've seen previously. All we're doing is we're adding this additional subscript for j to keep track of the fact that people are nested within groups, multiple groups. We're going to move from this level 1 model to the second level by having each of those parameters, the beta 0 and the beta 1, become outcomes in and of themselves at level 2. Okay, so these were the parameters that were estimated in level 1. We had an intercept and a slope at level 1. Now at level 2, we're basically fitting a new regression model for each of those school level characteristics. So the intercept, the average school intercept, is a function now of a new parameter that's supposed to be a gamma. It looks like a y, but it should be this Greek symbol here of a gamma, like a sideways fish, I guess. So this level 2 model is a new regression where we're saying this outcome variable is a function of an overall average, and then these mu's are residual terms at the second level. So now we have between group variability that's accounted for each outcome, the beta 0s and the beta 1. So each of these become outcomes at level 2 specified by their own regression equations. So if I kind of walk you through that again, we're going to build a model by linking those two models together. We specify first this within group individual level model where y is a function of an intercept, a slope associated with the variable x, plus residual variation. So these two parameters, the betas, now become outcomes in and of themselves at level 2. Beta 0 is a function of an overall intercept plus a residual term, and beta 1 also has a regression equation associated with it, saying that there's an average value for the effect of x on y plus some kind of random variation. So we're now dividing our model into fixed effects, these two overall averages, the average outcome and the average effect, or the average slope, I guess, of x on y, plus random effects. These mu's are random variability at the second level, at the between school variability, so that basically we're saying that there is, let's say, for example, a relationship between x and y at one school, and that may differ from the relationship of x on y at another school. So within each school, we're going to allow variability for the relationship of x on y, and then estimate the overall average as a function of the grand mean plus that random term. So how comfortable was all of that? Are there any questions about moving from that level 1 model to level 2? The conceptual idea behind it? Okay. So one of the key parts of ultimately building a multi-level model is we need to combine these into a single equation to help kind of keep track of what we're estimating in the multi-level model. So we're going to once again start with our single equation up here. Y is a function of beta 0, beta 1, and some random term associated with it. What we're going to do is use a little bit of algebra to substitute the values that we are identifying here in our level 2 model back up into the level 1 model. Okay, so remember that we said beta 0, which was defined at level 1, is a function of an overall average plus a residual term, and this beta 1 is also a function of an overall average plus a residual term. We're going to substitute this side of the equation basically into these terms up here. So this goes back to your basic algebra from high school. Hopefully you can remember. So we're going to start with our single equation. We have beta 0 and beta 1. And just use what's on the right side of the equation and substitute it in down here where we have beta 0 and beta 1. So now we've moved to gamma 0, 0 plus mu 0j, this part of beta 0, as our first term. And then we had beta 1, which is defined by gamma 1, 0 plus an error term. And it gets multiplied by x because we're substituting back up here, plus our residual. So far so good. We're just substituting, nothing too complex yet. The next step in algebra, we know we need to multiply these out. When we have some term multiplied by another term, we're going to multiply x by this and x by that to basically, I think it's called distribution. I can't remember my algebra very well. My dad would be upset with me right now. So we're going to multiply that out. So now we have gamma 1, 0 times x plus mu 1 times x. So just simply multiply x by each of those two terms, and now we're separating beta 0 plus beta 1 plus our residual. And now the last step is to separate our terms. We have a gamma here, we have a residual random term here, here's another gamma, here's another residual, here's another error term. So let's group these together so we can kind of keep track of what are called those fixed effects, the gammas, plus the random parts, the error terms. So we just simply rearrange things. So now we have gamma 0, 0 over here, plus gamma 1, 0 times x. Those are the fixed components. And we have over here all of the random error terms grouped together, the mu 0, the mu 1, and then the individual residual r. So these become fixed components, and those are random components. The key idea of multi-level modeling is that these error terms now are dependent on x, which once again violates our assumption of independence, because error terms are now complex. We need to account for that using multi-level models. So we've divided basically our equation into fixed effects and random effects. Fixed effects are basically the parameters that we're interested in. Random effects are error terms associated with that. So here's kind of what we're doing in a more concrete way. We're estimating a single equation of yi as a function of an intercept and a slope plus some kind of random residual across an entire population of schools. So imagine that we have some sample of, let's say, 30 schools. We're saying that in school number 1, some individual student's score is a function of an intercept plus that individual characteristic. Maybe we're looking at math achievement as a function of, let's just say gender, let's say. So X could be gender. So in school 1, a student's score in math achievement can be depicted as a regression where we have an intercept and a function of gender on math achievement. Maybe, let's say males do better on math than females. So there's a positive relationship of X on Y. The idea is that we can then collect data from multiple students within multiple schools, and each school is allowed to have its own regression equation. So the relationship between X and Y in school number 2 might be different than the relationship between X and Y in school 1. You can imagine that maybe in this school, there's a strong relationship between gender and math achievement. Maybe in this school here, this value of X on Y is very small. And we can continue on down and maybe get different types of schools. So this is depicting, hopefully, or should supposedly be depicting, this is like Little House on the Prairie school. This is the school that I went to in a small Iowa town, and this is like the school in a large city. But different types of students in different types of schools can expect different relationships between X and Y. Each one is allowed to have its own individual parameter, and there's variability of the relationship of individual level factors between schools. And that's what multi-level modeling is going to allow us to account for. So here's an example, if we're comfortable so far with the conceptual underpinnings of all that. The idea basically is that we're going to have individual variability, where we say gender affects my math achievement score. There's within person variability because we know that there's no perfect correlation, between gender and my achievement score. They were also saying that I belong to a school that within that school there's an average relationship between gender and math achievement, and that school has a different value perhaps than another school. So there's between school variability, and then there's the individual variability within students. So let's go through one example using the school level type of clustered data. So this is an example of a study that we published in Journal of Youth and Adolescence a couple of years ago, I guess now 5 years ago, 2010, where the research question was, does the influence of family level protective factors, such as parents monitoring and discipline practices, on the target adolescent substance use vary in different school contexts? So this is our relationship at the individual level. Students' reports of parents monitoring and other practices on their alcohol use or other substance use. And wanting to know, does that relationship differ depending upon different types of school contexts? So we were very lucky to have, in Pennsylvania, a very large data set of nearly 50,000 students in grades 6 through 12, or 6, 8, 10, and 12. So every other year, students are administered this survey. The students are nested within 192 schools. So we have this nested structure of students nested within 192 schools throughout the state of Pennsylvania. Our outcome variable was past 30-day use of alcohol, cigarettes, or marijuana. For this particular study, we treated the outcome as dichotomous. This, once again, is where the SAS or SPSS syntax gets more tricky than what we need to talk about today. You need to, and it is possible to account for different types of outcome variables, categorical, continuous, in these models. For now, let's just brush aside that fact and just pretend that we're just looking at some outcome variable and not worrying about what the distribution was. But we're using logistic regression now to predict either they used or they did not use a particular substance in the last 30 days. The technical details of how to do that versus a continuous variable are to be continued, I guess.
Can you do this in M+?
Yes.
Yeah, of course. I thought you...
Yes, M+ does allow and is fairly straightforward in fitting multi-level models. Yep. I did not use M+ for this. So our X variable, our predictor variable, this is where we need to spend a little bit of time thinking about how this predictor variable is conceptualized. It's students' reports of family protection factors. So their parents' attachment to the child, the parents' use of supervision and discipline. So students answer questions basically saying, yes, my parents supervise me, or yes, I have a close relationship with my parents. You can imagine all those different items on a survey. So students answer those questions about their parents. That's our level 1, student reports. We created what are called school level aggregates to create level 2 versions of those same variables. So in other words, at level 2, we took all the students in one school and averaged the scores within that school to create a school level aggregate. So in one school, we might have fairly high levels of students' reports of supervision. Another school, we averaged, and maybe on average, those students report less supervision. So we have some aggregate level score at the school level as our school level variable. So we're just creating a mean based on the students within that school to define a level 2 aggregate of the same variable at level 1. So the same variables are used at level 1 and level 2. Level 2 is just a group level mean, basically, a school level mean. We're going to start with that one-way ANOVA that we spent some time talking about in the ICC world. This ANOVA is used to estimate the interclass correlation and test the hypothesis whether all of the J number of schools have the same mean and whether or not we should be accounting for this nested structure. So here's a real quick walkthrough in this unconditional model. We're going to simplify our regression equation now to what's called an unconditional model, meaning that there are no predictors. So at level 1, our individual students' outcomes are a function of just an intercept and a random term. This intercept, remember, becomes an outcome at level 2. It's also a function of a grand mean intercept or a grand mean average plus a residual school level intercept or school level residual. So basically we're saying that in a combined model, a student's outcome on alcohol use, let's say, is a function of the student's own average, a grand mean overall school average plus group level error and person level error, based on these residual terms. So we have a residual at the within person and at the between person level. And so those become components that we're going to fit into the ICC equation. So we have between group variance depicted by the group level error and the within group variance depicted by the individual level error. And those are used to estimate the ICC. Did I lose anybody? Nope? Okay, good. Let's keep moving as much as we can. Here's the results of that ICC computation. I computed ICCs for each of the 3 outcome variables of alcohol, cigarettes, and marijuana. And I did this across the entire sample of schools. ICC for alcohol was the highest of 0.10. Here's the formula that I used. There was between group variability equal to 0.11 and within person variability of 1.01. So when I do that simple addition, I get 0.1 divided by 1.11 equals basically 10%. So the bottom line is saying then that 10% of the variability in alcohol use is due to the fact that students attend different schools. That's a pretty large proportion of variability, if we think about it. That means that if we just took 100 students at random, let's say, or if we took 1 student at random, and we said, let's assign you randomly to a school, and then another student we randomly assign to another school, and we do that multiple times, if we're just randomly putting students in different schools and then looking at their alcohol use in the last 30 days, 10% of the variability in whatever they report for alcohol use is going to be due to the fact that they attended this school versus another school. That's a pretty big amount of variability, meaning that whether or not you attend one school versus another school has an effect on your alcohol use. It has less of an effect on their cigarette and marijuana use, but still significant, I would say. And then also we looked at the ICC of that Family Protection Index. 17% of the variability now is due to between school differences. So in other words, if you attend one school, the level of supervision and monitoring that you receive is different than if you attend another school. The parents of different school children basically differ in terms of their parenting. A lot of it's due to basically neighborhoods. You would imagine school is now a proxy for neighborhood conditions, I would imagine, poverty or whatever SES. So these are basically results that tell us, yes, we should proceed with a multi-level model because clustering And within group variability is definitely a problem. There seems to be relationships that are due to higher levels of our data. Namely, students are going to different schools.
So you're just using school as class, you're not using classroom as class?
Right, school is a proxy for the class. We don't have individual classroom level data. We just know that students attended school 1 or school 2. So my next step is to specify predictors at both of these levels. So now that we've found that there is significant within group correlations that need to be accounted for, the next step was to estimate this model that has the predictor of family protection. I've identified that, or abbreviated it with FP. So at level 1, I'm saying that a student's past 30-day use of alcohol use is a function of intercept and the effect of family protection. So individual scores, my parents supervise me, they monitor me, I have a close relationship. That affects a student's score on alcohol use. And then at level 2, because each of these two terms now are brought down to the level 2 model, the overall average intercept is a function of a school level grand mean plus a school level characteristic now. This is that aggregated mean of family protection, of the average level of family protection at this school. And then another school is going to have another average value of family protection. So basically, I'm using school level average protection as a predictor of both the intercept and the slope associated with family protection at the individual level. So this is saying, if we combine these equations using that algebra that I showed you in the earlier slide, and we end up with this result of a combined model, we're saying that a student's substance use in the past 30 days is a function of the following terms. It's a function of the school level average overall. So some schools simply have more substance use than others, right? So a student's score is going to be affected by the school level average. A student's alcohol use is also affected by the school level of family protection. So belonging to a school that has higher or lower levels of family protection has an impact on my alcohol use. My alcohol use is also a function of my own individual family protection. So what my parents are doing. So that's my individual level predictor. And then finally, because of the way that this substitution occurs, an interaction between the school family protection and the individual family protection. So now we're saying that my individual substance use is a result of the interaction basically between school level and individual level family protection. So this is what's referred to as a cross-level interaction, which is answering the question of, do school level aggregate of family protection predict the level 1 slope associated with the individual students' scores of family protection? Or in other words, do student level and school level family protection interact to predict an individual's own substance use? So that's that interaction, school level times individual level. Here are the results of our models where we have, in this case, the dependent variable of alcohol use, several independent variables. We included gender, a measure of free lunch at the school as an SES indicator, individual family protection, school level family protection. The S by F interaction is the school level by family level protection interaction that we're interested in. That's the cross-level interaction that we're most interested in. We divided the results by 6th, 8th, 10th, and 12th graders because we know that there are probably differences developmentally in both of those outcomes. Alcohol use is much more common as you get older, and also parents probably interact with 6th graders differently than they do with 12th graders. So we didn't think it was wise to put everybody into one data set. We wanted to separate results for each group. And interestingly enough, we found that there was a cross-level interaction at the 10th grade and the 12th grade, not for the earlier grades. So we're seeing here that, in this case, family protection is, these are odds ratios, remember, so there's an odds ratio of 0.66, 0.64, 0.5, 0.68, saying that higher levels of family protection are related to lower levels of substance use. In some cases, there's a similar school level protection, but in those higher level grades, there's the interaction between school and individual level. So we graphed that. This is showing you the results of the family level protection for 3 different types of schools. Schools are defined by the overall average school protection within that. There's either, we used plus or minus 1 standard deviation from the overall grand mean. So this is dividing schools into 1 standard deviation above all other schools, or less than 1 standard deviation below all schools. So these are basically saying that these schools over here in the 1 column had extremely high levels of family protection. Those parents in those schools are doing a great job of supervising, monitoring their students, or their parents, or those parents are doing a great job of monitoring their children. On the other hand, some schools are defined by parents that are not doing so well. They're at the -1 level in terms of average school level protection. And the bottom line is that the effect of family protection varies depending on what type of school the child is in. At average or high levels of school level protection, family processes work as you would expect. They're below the line of 1, so family protection is related to lower levels of substance use. However, in the high-risk schools, high risk defined by parents who are not monitoring and supervising their children, you see that there is increased positive odds ratios, saying that at low levels of school protection, family protection did not help prevent the students from using substances. So there was a opposite effect, basically, that if schools don't have parents who are doing the correct things, those students are more likely to use alcohol or cigarettes or marijuana.
Well, what happened to free lunch is the proxy?
Free lunch, I don't believe it was significant for hardly anything.
So you can't really make an SES case here, can you?
Not when you control for all these other variables. Yeah, so that was interesting. That free lunch did not do much. And it did not interact with family level protection either. So it's 4 o'clock. Should I stop or keep going?
How much more do you have?
Just a few more slides, not much.
You guys are doing that?
Keep going. Love it.
Keep going?
Yeah. Yes.
How about anybody that needs to leave can leave. I won't hold it against you.
Are you good for a few more slides?
Yeah, I'm good for a few more slides.
I think we are too.
So, yeah, this is actually, I think, the more, I wouldn't say common, but this is probably the more easily understood type of multiple level.
And Wally, thanks for coming.
Okay, so let's keep blasting through. So, remember we talked at the beginning that other situations of nested data can occur. One of those situations being when we have repeated measures of individuals with longitudinal data. So we're now going to focus on this type of scenario. The concepts are the same in either scenario, but things change a little bit. And unfortunately, the Greek symbols that we use, like those gammas and the betas, the literature, when you look at these 2 different literatures, use different Greek symbols. It's the most frustrating thing in the world. If you go to the educational research world and read articles, they'll use one set of numbers or one set of Greek letters, and when you go to the repeated measures world, they'll use another set of parameters. So it's more confusing than it needs to be, but understand that the concepts are the same across both scenarios. So let's talk about this example here where we have individuals followed for 3 points of time, 3 observations. So longitudinal data analysis is once again a situation where we have problems with these repeated observations exhibiting correlations. Probably now even more likely to be kind of an issue, because if you ask someone about their alcohol use at time 1, ask them about their alcohol use at time 2, and at time 3, it's the same individual answering that question all 3 times. So there's some type of dependency in those outcome variables and there are errors associated with that because it's the same person across multiple ways of data. And so that within-person correlation should be accounted for because we now have dependency of observations and errors. So we violated that assumption once again. So we're going to treat the repeated measures as level 1 and then treat people as level 2. One of the practical slides that I decided to keep in for this presentation is the idea that when you move into this longitudinal data analysis, repeated measure analysis situations, data management becomes very important. We kind of touched upon this earlier when we talked about IDs for students within classrooms. Not only do you need to have that for this type of analysis to work, you also need to have the data in the correct format in your files. So this is how you normally probably look at your data when you have SPSS or SAS or Excel, whatever. You have student 1, student 2 on down the line, you have numbers of students, and then you have columns for each variable, right? This is how we kind of organize our data. So this is a situation where we have students measured across 6 different semesters with college GPA at semester 1, 2, 3, 4, 5, 6. We have a measure of high school GPA as well, and then other variables. But the idea is that longitudinal data are kind of indicated by these numbers of wave 1, wave 2, 3, on down to wave 6. That's how we normally treat our data. If we use multi-level models on this data, like in this format, we will not be able to conduct the analysis. We need to restructure the data, in other words, into what's called a person period data set, where we basically flip the data. So now, instead of going across, we have going down. So student 1 now has 6 rows of data with an ID that's common to that particular student. Occasion is our measure of time. So they're measured at wave 1, 2, 3, 4, 5, 6. And here's the GPA score associated with each wave. So this is called a person period, or sometimes called a long data set, because we're now basically going down instead of across when we're adding waves to the data. So this is important because we need this to keep track of variables that change across time or stay the same across time. So just a quick aside. Not necessary to understand what's happening next, but wanted to put that in there. So when we move to this repeated measures world, what we are estimating is called a growth curve, or a growth curve model is typically an analysis that's used for repeated measures where we're specifying this type of relationship that we've drawn in that normal regression, and we're defining it as a growth curve where the x-axis is a measure of time and the y-axis is our outcome variable that's depending upon time. And so the goal of a growth curve analysis is, first of all, to describe the shape of that growth curve. Does it increase? Does it decrease? Does it stay the same? So imagine something like alcohol use across the ages 12 to 18 as a growth curve model. You would probably have expectations for what the shape of that trajectory would be like. Typically, you would expect kind of a positive trajectory where alcohol use increases as you get older. So there's going to be a positive trajectory associated with time in that case. We also then, once we've identified the shape of that growth curve and described how it changes, we can add predictors that explain that growth curve. They can be both time invariant and time varying. Time invariant predictors are between person effects, something like gender, something like maybe some demographic variable that you measured at time 1. Those stay the same at each wave. And you could also include time varying predictors such as maybe an individual's, what could be a time varying predictor of alcohol use? Maybe their peers' alcohol use. So that can change at each wave, and that's a within person effect because it changes within a person across time. So here's the new model that we're specifying at level 1. So this is the new Greek symbols. These are now pi's. So we're saying that I1 at level 1 is a function of an intercept and a slope associated with time. So the growth parameters are the model of intra-individual change, how individuals change across time, where an intercept is depicted by pi 0, and the slope, the rate of change, is depicted by pi 1, which is a function of time, basically. And the idea is that intercepts and slopes are varying across individuals, across persons. Each person has their own change trajectory. So not every adolescent has the same pattern of alcohol use. Some adolescents may have rapidly increasing trajectories of alcohol use as they go from 12 to 18. Other adolescents may start out using a lot of alcohol and then stop using alcohol. And others maybe stay flat and never use alcohol. So you have different types of trajectories depending upon individuals. Same thing, at level 2, each of those outcomes becomes their own model. So pi 0, the intercept, and the slope now become predicted by overall averages. Once again, we have new terms for the errors. These are zetas, depicting level 2 variability, but just once again know that these are residual error terms at the between person level. Between person residuals basically say that allow that trajectory to differ between one person and the next. And we can now add variables, predictor variables at each level. So at at level 1, we can add some type of individual level predictor. So we have time as our first predictor. Our second predictor could be, as I said, maybe peer alcohol use that changes across time. Could also be a predictor. We can also then add time invariant predictors at level 2, where we just expand this equation to include some type of between person predictor, in this case depicted by z's. So this might be easiest if I walk through the example. The example that I'm showing you is from a study in child development from several years ago. The idea is that there was a sample of 103 children born to low-income families who were assigned to different intervention to an intervention program. Roughly half were assigned to an early intervention program, and half were assigned to a control group. Each child was assessed a number of times between 6 and 96 months. We're going to analyze just 3 ways of data here, 12, 18, and 24 months. And the question is, what's the effect of attending that intervention program on children's changes in cognitive ability, or some type of cognitive performance test? So does belonging to some type of early intervention, like Head Start, let's say, have an effect on children's performance across the first year, couple of years of life, between 12 months and 24 months? So here's just the showing you what the data set looks like. We have IDs, they're hard to read, I'm sure, in the back, but we have 3 waves of data from each individual that keep track at age 12 months, 18 months, and 24 months, although there's variability around that. Here's our cognitive score, so this is our outcome variable. Depressingly, it shows that in most cases, this performance, which is a kind of a standardized, nationally normed scale, these children are showing decreasing performance across time compared to national norms. And then we have some type of time invariant predictor of whether or not they belong to the intervention program or not. So 1 or 0. This is showing you what we're really doing conceptually. This is each individual student or each individual child has a growth trajectory of their cognitive performance across these 3 waves of data. So this is just a random sample of 8 students and the scatter plot of age and their cognitive performance, showing you that it looks like in a lot of cases there's a negative slope showing that cognitive performance is decreasing, or this cognitive ability task is decreasing across time. And in most cases it's fairly linear. The red lines are showing that maybe there's some type of curvilinear relationship for some students. But the idea is that what we're going to do is estimate a model where each child has their own growth trajectory, each relationship between their age and the cognitive performance skill, and we're going to estimate the variability of the number of students around those average scores of trajectories of individual change. So at level 1, we have this cognitive performance skill as a function of an intercept, where they are at age 1. So pi 0 is the average cognitive performance when a child equals 1 because we've centered age. We have a slope associated with age. This is showing a positive relationship, so as age increases, cognitive performance is also increasing. We just showed in the last slide that this may be truly more accurately depicted as a negative slope. And then we have error terms associated with that, so that each individual's true change is a function of these residuals of these observed scores. So we've observed a score at time 1, time 2, and time 3 that we fit a trajectory for each individual student. So we're defining this fitted trajectory as their true score, their true change score, if there was no error terms. And when we look across the entire sample, here's the same plot of everybody kind of piled onto one graph. We see that in most cases, most of the children are declining across time. There are some who, however, are increasing, and some are starting out very low, some are starting out high. The key idea is that there's a lot of variability in these slopes, right? If we just took one overall average, we are not accounting for a lot of between-person variability in this change. So we want to be able to account for the fact that some students start high, some students start low, and that there's a lot of variability in the rates of change across time. So we're going to do that by fitting a multi-level model that has level 1. The cognitive score is a function of an intercept and a slope. And then for each of these outcome variables, the intercept and the slope, we're going to predict that outcome by their participation in the program. So the initial status is a function of an intercept, overall average, plus whether or not they belong to the program, and error residual. And then this outcome here, the slope associated with age, is also a function of an overall average plus whether or not they belong to the program. Here are the results, the fixed effects, the fitted model for initial status. So here's our model, level 2 model for the intercept. It has an overall average of 107. It's significantly different than 0. And then there is an effective program on the intercept, which is also significant. So it's basically saying that overall our sample, students start out with an average score of 107. If they belong to a program, that intercept is higher. if they were assigned to the treatment program, basically. So there's a positive effect of belonging to a program on where they started out. We also have a model for the rate of change, an overall average of -21, saying that on average, students' cognitive performance skills are decreasing across time. However, there is an effect of program on that that is significant, saying that it flattens that downward trajectory. It pulls it back up by a value of 5.27. So we can most easily conceptualize this by fitting values where we substitute in program is either equal to 0 or 1. So here's our fitted model for the intercept and the slope. And we can imagine, or we can use an indicator of 0 for those who do not belong to the program and 1 for those who do belong to the program to estimate fitted lines. So in the case where program equals 0, those who were assigned to the control condition, here's their predicted cognitive score. 107 is their intercept, and then they change at a negative value of -21 as they're increasing in age. So their slope is associated with -21 change in outcome for every year of age. When we substitute 1 for program, we're now going to get a new fitted line for the program group where basically the intercept is now 107 plus 685, so that equals 114. That's the purple line here. So those who belong to or assigned to the program had higher average starting values, and then their rate of change is -21 plus 527, resulting in a less steep slope of -15. So somewhat depicted here as a less decline across time if they were assigned to the program. So the tentative conclusion is that those who were assigned to the intervention program appear to have higher initial status and slower rates of decline. That's a function of belonging to the intervention group or not. So those are the examples. Should I maybe stop here for a second? Are there any questions about that conceptual basis or underlying model building that we took to fit these models? I know we skipped over a lot of things. Like I said, this should be 16 weeks instead of an hour and a half. But hopefully it's meant to
Maybe a little
get
more
you
advanced.
excited.
My understanding is that growth curve modeling has an assumption that there's a developmental process going on there.
Good question.
Otherwise, it doesn't really necessarily.
Yeah, if we go back to this here, the growth curve model, one of the first steps that you're going to do is you're going to estimate what the shape of these lines is like. A growth curve model assumes that time is a significant predictor of the outcome. That's a assumption you should test, I guess, to see what the slope is. If the slope is not significant, it means that it's a flat line across time, that the score doesn't
But
change.
isn't there also, because I mean, part of this comes from all my work with Jim Jackard, as you probably know, but there's a conceptual thing that if you're dealing with the process that really doesn't have a developmental thing to it, you've got to be a little careful
Ah,
with this.
so what if we had something that looks like this instead? So here's our normal growth curve where we have some kind of positive increasing, or we can have a negative decreasing, or a flat. We can also have something that looks like this.
Right.
And then, so this is now time, and this is our outcome variable. In that case, we have what's called a fluctuation model. In that case, we just remove time as a predictor, and we can move forward with a multi-level model and still predict the change in Y as a function of both time invariant and time varying predictors.
But one reason I bring that up is because sometimes people apply growth curve modeling to inappropriate situations, and I've reviewed a few things.
Yeah, because that first step,
You
you
gotta
have
think through,
data.
before you get into this, you gotta think through.
Yeah, you have to take that first step and see what's the change. You need to describe the shape of that trajectory. Is it positively increasing, negatively decreasing, staying flat? Or is it doing something like that that's not dependent on time? and it just randomly fluctuates throughout the day or throughout a number of days, whatever.
But in place of growth model, can we use nonlinear regression? In cases where you had
regression?
in cases particularly the point Dr. Hillhouse has made, and also your 6 graph where 3 of them were red. The reason they were red because of this point he made, that over time, what about we use nonlinear?
Yes,
to
yes. So
explain?
if you should explore the fact that maybe this growth is something other than a linear straight
Yeah.
line. You should explore the fact that maybe it's curvilinear,
Yeah.
a polynomial. You could have
Polynomial.
time squared or even time cubed to account for those different type of trajectories.
That's still growth curve modeling.
It's still growth. Yeah.
The way you handle, I have a grant in that's doing this. If it doesn't have a developmental process, you use something called cross-leg panel design, which I don't know if you're familiar.
I actually would say you should use multi-level modeling still and just model the
You should talk to
fluctuations.
Jim Jackard, my statistician.
Use what's called, I would use what's called fixed effects regression.
The cross-leg panel can also work, so we got that. We still.
I would have a discussion with Jim about that.
You should have a discussion. I want you to have a discussion with Jim.
Yeah,
But it's another way of modeling effects across time.
yeah, yeah.
Out of curiosity, just looking at your data and not the methods, I mean, I know you try to give this example to illustrate methods, but just looking at data, how different are those slopes? If we use the family of curve analysis, it's just baseline. They start out, people who receive training, they happen to be at the higher level of
Right, and that's
they
one of
perform
the
better.
issues with this is that
Yeah.
they started out different.
Yeah.
You didn't start the
So there
training in
wasn't
6
any-
months?
Yeah, and that's-
Understood this right? So you're
yeah.
coming in and measuring not at time point 0.
Yeah, we're 6 months after the intervention started, so there's already some gains that may have occurred.
So some people gain more rapidly, and probably they are the purple
Yeah,
ones. And some-
right. That's probably
Maybe.
true. Yeah.
So, yeah, the findings in this one are kind of counterintuitive, aren't they? I mean,
Yeah.
I think
They
that
don't-
there'd
yeah, no.
be, that to be some improvement rather than a lack of
A lack of
or I
decline.
guess a reduced worsening to the problem.
Mhm.
Huh.
Well, that's a treatment effect, though. You know, if people are getting worse and you make them get worse
Yeah.
as quickly. That's
Yeah, it's something like if you,
Like, this was Alzheimer's, for
Yeah,
example.
Right.
because there's something else going on that's causing them to get
right,
worse.
yeah, if there's cognitive decline as you get older, if you can do something to dampen that decline, slow it down, then that's a positive treatment effect. I think my last few slides are just simply showing you where to go from here. So there are many statistical software options for fitting these models. SAS, SPSS, M+, MLWin, all kinds of things. And software has come a long way in the last 10 years when I first learned these methods. As we mentioned in the earlier talk, they can handle missing data, they can accommodate non-normal data, so there's lots of options that are available for kind of going outside of the normal box now. What I would do if I were you and wanting to learn these methods, I would start with a couple articles. Judith Singer is probably the guru for fitting these latent growth models or growth models. She's written both a book and an article for using ProcMixed that was followed up by 2 authors who replicated her results using SPSS. So these give very practical hands-on advice for fitting these models in SAS and SPSS. There's also a very good primer on multi-level modeling written by Andrew Hayes at Ohio State, which I would recommend as a good way to get conceptual understanding of these models. There's also a very helpful website maintained by UCLA that has lots of statistical support, not just for multi-level modeling, but for all kinds of things. So I would recommend visiting this UCLA website. Once again, I'll send these PowerPoint slides so you can have this as a way to really get into some of these techniques. It actually gives many options for multi-level modeling, including the analysis for Judith Singer's book called Applied Longitudinal Data Analysis. This is the book that I use as the basis for my class when I teach. It's very hands-on, easy to use, and very practical. So I would recommend this book as a good starting point as well. And I think that's it. So I think I've been talking for a while.
Thank you, Michael. I gotta say, the day has flown by. It's been one of those days where you're just very energized and stimulated by the content, and I just really appreciate the just the effort that you put into communicating these ideas and coming down and doing it for us. Thank you so much.
Very well.
I also have to say, Angie Hageman was thrown quite a curveball when it came to scheduling this and rescheduling it this week. Michael was delayed by a day coming out of Pennsylvania because of the snowstorm, and so we had to kind of reconfigure everything. And I gotta also thank Colin Chesley for actually. He didn't need to do this, it turns out, in retrospect, but he did move his class today, and so we were able to camp out here all day long. But anyway, thanks so much for coming down, and I guess we can follow up with you with through the .art team, but if you have individual questions for Michael, shoot me an email. But
like I said, I'll send all these slides to Angie, who can distribute them to anyone who would like them.
we have a folder going on the either the working group website or the .art website that has all of his slides from last time, as well as other resources. I've asked Angie to order the book that you recommended from the last time, was directed at